going to discuss about the calculation of delta knot for tetrahedral complexes. So we have two questions here. Electronic spectra of tetrahedral complex cobalt Cl42 minus gives absorption band set 5800 15,000. Find out the delta knot. And the nickel chloride complex, we have two absorption bands, so we have to calculate the delta knot. So before going into these problems, so we have to know about the oracle diagrams. So oracle diagrams are different for octahedral complexes and tetrahedral complexes. Okay, so when we have a D1 configuration, so the oracle diagram will be this: 2D, we have a T2G to 2EG. So whereas for tetrahedral complexes, this will become E and T2. So tetrahedral complexes are not having center of inversion, so because of that reason we will remove this G. We just take this one. So we just need to reverse the oracle diagram for we just want to reverse the oracle diagram of octahedral complex into tetrahedral complex. So whatever we have, that we just reverse, then it will become a oracle diagram for tetrahedral complex. So now we'll go cobalt +2. So here cobalt is in the +2 oxidation state. So if you want to draw the oracle diagram for tetrahedral complex, so it's better to draw the oracle diagram for octahedral complex. So from there we can reverse it, so that will be easy. So here we have cobalt +2, 4s0 3d7. So this comes under electron promotion. So this will be opposite to the f orbital splitting in a octahedral field splitting. Opposite means this T1G, T2G, A2G, this is T1G, this will be 4P, 4F, here 4, 4, 4. So this is for the octahedral complex. So now we need to draw for the tetrahedral complex. Just reverse this one. This 4F will be there, 4P will be there. So here the highest energy will become lowest energy in a tetrahedral complex. Just reverse it. A2 is high here, and in this case A2 comes down. Then T2 will be here only, and T1 will comes here, and 4P, T1 goes here. Okay, so this is the oracle diagram for cobalt Cl4 -2. And now we need to know the energy values also. The energy of this A2G is plus 12 dq, this is plus 2 dq, this is minus 6 dq. So whatever the positive values are there, they will become negative values in a tetrahedral. So here it is positive, here it is negative, it will become a positive here, 6 dq, this will minus 12 dq, this is 2 dq. Okay, so this is the oracle diagram, overall oracle diagram for cobalt Cl4 and here we can see another change, one more observation here. This is called crossed, and this is called non-crossed transition, crossed transition. So non-crossed transition, when we will see, when we have two same terms, that time we will say non-crossed transition. Whereas two different terms are there, means that time we will say crossed transition. In octahedral complexes it is a crossed, whereas in tetrahedral complex, I am talking about D7 in octahedral complexes, it shows crossed transition, whereas in case of tetrahedral complexes it shows non-crossed transitions. Okay, so now here three transitions are possible: one transition, second transition, and third transitions. So I will write all these transitions here: A2 to T2, A2 to T1 of f orbital, and A2 to T1 of p orbital. This is for p orbital and this is for f orbital. So among these three transitions, this comes in the IR range, IR spectra. So this we cannot use to calculate the delta knot. For I have made a video for delta knot for octahedral complexes. There I have taken only first transitions. So, and here we can use any of these transitions. Okay, so in tetrahedral complexes we mostly use second transition, that is A2 to T1. Okay, so in this question they have given two transition, so third one they did not give. So the one which is not given, that is in the IR range, range. Okay, so this 5800 is for this second transition and 15,000 is for this third transition. Okay, so now we are taking this transition. So the energy of T1F is how much? This 6 dq minus the energy of A2 minus 12 dq is equals to 5800. So this will be 18 dq equals to 5800. So dq will be 5800 by 18. Imagine that some x will come answer. So just multiply both the sides with 10. So 10 dq will be 10x. 10 dq is nothing but delta knot will be 10x. So this is the answer. Okay, I am not calculating this value, I have written directly. And we have another example here, sorry, another question we have for nickel Cl4. Okay, so nickel Cl4 minus 2, it's minus 2. So this is nickel plus 2. So first draw for the octahedral complex. This is 3F, this is 3P. So this comes under whole inversion. So similar to the F orbitals between in octahedral complex. This will be A2G, T2G, T1G and T1G. And now this is for octahedral. For tetrahedral we have to just reverse the spectra. So T1 comes down, T1, T2, A2, A2 is here, this is T1P. Okay, energy 12 dq minus 2 dq plus 6 dq, and the same energy here, this will be minus 6 dq. Whatever negatives are there, they will become positive. 2 dq and 12 dq. Okay, so here also we have three transitions. So T1 to T2, T1 to T1P, T1 to, sorry, this is T1 to A2, T1 to T1P. So here also this transition comes in the IR range. So here they have given only two transition, that is for this transition and 14,000 is for this. Okay, so here we'll take this value, this transition, to calculate the delta knot, and A2 energy is 12 dq minus T1 energy is 6 dq is equals to 7,800. This will be 18 dq, 7,800, dq will be 7,800 by 18. Some x will come, just multiply from both these sides with 10. This will be delta knot will be 10x. So this is the answer. So this is the way to calculate the delta knot for tetrahedral complexes. First we have to show about the Argel diagram. Just whatever Argel diagram is there for octahedral complex. If you learn Argel diagram for octahedral complexes properly, then it's very easy to calculate for the tetrahedral complexes. I have a to just identify ground term and For to identify ground term, I have a small blind indication. Just take D2. So D2 is involved 3F and 3P. So there is a confusion whether T1G or A1G, A2G. There is a confusion which one is the ground state. Just remember. So this is T2G and this is EG. So 2 electrons are there. So how many vacant orbital is here? Only one. So T1G will be the ground state for D2. Okay, because one vacancy is there, T1G. Just remember like that. And for D3, here no vacancy is there. So just remember A2G. If vacancy is there, the term will be T1G because it is also T, it is also T. If no vacancy, then it will become A2G. Now if you remember these two, for D7, D8 also it's very easy. D2 is opposite of D8 and D3 is opposite for D7. That's it. For D1, for D1, D6, D4, D9, these are very easy to remember, but there will be confusion among these four. You just remember in D2 one vacancy is there, the ground term will be T1G. D3 no orbital vacancy is there, so A2G is the ground state. Just remember D2 is opposite of D8 and D3 is opposite for D7. And here we can see this is for D8 octahedral complex, and here in D2 T1G is the ground state. Just opposite to that, A2G is the ground state in D8. Okay, and this is for D7. D7 T1G is the ground state, whereas here in D3 A2G is the ground state, just opposite. So this is about the delta knot for tetrahedral complexes. Thank you.